Astronomy and Sciences Department of Ankara University, where he also went to grad school there. And he's also teaching there right now. And his research interests include extrasolar planets and eclipsing stars. And today he's going to be talking about 2 new exoplanets him and his team have discovered. So.
Okay, great introduction. All right. Thank you. All right, so I'm going to talk about the exoplanet discoveries with the timing technique, actually. Right. Not just the 2 new discoveries, but in general. Right. So let's start with the definition, of course. All right, so an exoplanet is a celestial object that is less massive than 13 Jupiter masses, which is the mass limit for deuterium burning. All right, so this is H2, as you know, hydrogen 2. All right, so there is a mass and pressure limit to burning. All right, and after 80 Jupiter masses, this thing becomes a star. Between them, it is called a brown dwarf. All right, brown dwarfs are failed stars. They can fuse deuterium, but not hydrogen itself. Right? For that, they need 80 Jupiter masses. So they got to be below 13 Jupiter masses, but they got to be massive enough to keep a spherical shape, due to the gravity. And this is a bit complicated, the lower limit, because it depends also on the density. But there is no orbital definition here, as you can see. So we don't say planets outside of our solar system orbiting other stars, because there are planets that do not orbit other stars. All right? These are called free-floating planets. So there are starless planets as well. So we are looking for them to understand planet formation, like our solar system formation, and also to find life. Of course, that's the ultimate aim, right? To understand if we are alone in the universe or not. But it's like looking for a needle in a haystack, right? So it really is challenging because there are many objects out there, and planets gotta be very faint, right? Because they are small, they are cold, so they are much fainter than stars and brown dwarfs. So even brown dwarfs are very difficult to find, and planets should be very hard to find. But with smart techniques and with sufficient technology, we can find actually exoplanets. So if you know what we do, then there's no reason to find out. But the first discoveries came really accidentally. And not just by one accident, by 2 accidents. So the first one is a real accident. So William Boltzmann and his team were observing pulsars. These are neutron stars, the very core of massive objects, massive stars between 8 and 25 solar masses. And he is not an exoplanet astronomer. There were no exoplanets at the time. These are the first discoveries, of course. And he's not into planets. He was just looking for neutron stars with this radio telescopes, because neutron stars are observed in radio. And this is the Green Bank 300-foot telescope, which got this shape in 15 November 1988. So one morning, they come to the observatory and they find it in this shape. So they had to move on, of course, and they moved on with their research, and they proposed a project to the Arecibo radio telescope in Puerto Rico to of course, observe their objects. But the second accident is that at that time, this telescope was also in safe mode. It was not working properly, it was not able to look at all the directions, but just, as they call it, the zenith point, so above your head. All right, so it was able to just see what's on top of your head. And so he decided to count the pulsars that could pass from the zenith point. What else to do, right? So he proposed a project because there were not so many people interested in the safe mode. He got a lot of time, and he started to work on his project, started to find the neutron stars. Neutron stars are interesting objects. They have a very strong magnetic field, and the charged particles follow these magnetic fields, and since they lose angular momentum, they radiate. Okay? And these radiations are actually detected in the radio waves bands, right, by the radio telescopes, like the Andrew-Ostrom's building was using. All right, so these objects are very fast rotators. They just rotate about their axis 1,000 times in just 1 second, because they're very small and they're very dense, right? So imagine over 2 solar masses in just 20 kilometer size object. Okay, that's what neutron stars are, and because they inherit the angular momentum of a huge star, for which they play the core role, and that star had a supernova explosion, and it left behind this small object, and it inherited this angular momentum, so it rotates around its axis very fast. Right? So they just wanted to know the rotation rate, which is 6 milliseconds. So it is a fast rotator indeed. But it turned out that the rotation rate is changing. And the rotation rate is changing very periodically. Not just by 1 sinusoidal, but 2, then 3 sinusoidal as they find out. All right? This was back in 1992. All right? So how come this rotational period changed? Because nothing known at the time to cause such an effect in the rotation rate of a neutron star. This has got to be very, very stable. Right? So the explanation is that actually it's very old. So people back in 17th century were observing Jupiter and the moons of Jupiter. This is Io in particular, but the other large satellites, there are 4 of them. And Ole Romer, the Danish astronomer, found out in 1676, by the way, it was almost 7 years or so after the first observations of the moons, the satellites of Jupiter, by Galileo. Okay? So it was very old. And he found out that as he observed the occultations or transits of Io by the Jupiter disk, he found out that these times are also changing. How come? How can the timing of the observation changes? Because this has got to be a mechanical system. It should work like a clock, right? But there is, in fact, a large amplitude variation and the periodical. So he argued that because Jupiter has an orbital motion and the Earth has an orbital motion about the Sun, their relative positions changes, right? Their relative positions change in time during one full orbit, and because these distances changes with the positions, and the light has a finite speed, which was known at the time. People knew that the light had a finite speed, but they had very hard time to measure it, because the objects on the Earth's surface are very close to each other, and the light is very fast, the photons are very fast. right? As we know today, 300,000 kilometers per second, right? It's a huge velocity that you can precisely measure in laboratories, right? At that time. So, he argued that because the speed of light is finite, but the distance changes, when you observe an occultation from this point, then it will take longer time for the light to reach your telescope than this position. Okay? So the occultation here will be observed later than an occultation here. So this will change. This is called the light time effect, or to honor him by Romer delay. Right? This is not just the delay, of course, it changes with time back and forth. But yeah, this is the main principle. So the neutron star that they were observing, this is the telephone number, 1257 plus 12. Should have been orbiting around the common center of mass with not just one body but two bodies. Right? So because it orbits around a common center of mass with, it turns out that planetary mass bodies, it comes towards the observer and it approaches you, then you observe, you get the rotation signals. These are pulses. These are pulses, the radio signals from the poles of the neutron stars. As this pole is directed towards you, then you get a radio signal. And when it goes away from you, the signal goes away. Right? So these are just like peaks, repeating with this rate. Supposed to be repeating. But it is changing as it is. Right? So as it approaches you, the star, because we are oversimplifying things, right? When we say planets orbit the stars. Planets and stars orbit the same common center of mass, right? But because stars are massive, much more massive than the planets, this common center of mass are closer to the star. Okay? In our case, it is actually inside the sun, all right? So the sun doesn't move much. Okay? But in that case, it moves. And as it turns out, you can observe this motion from the rotation rate, from the change in the rotation rate of the neutron star. That's interesting because when it is closer to you, you get these signals earlier. When it is away from you, you get these signals later, right? And it changes, okay? As it orbits around the common center of mass, the star. You don't see the planets. You don't see the planets at all. Right? You just see the star. You just observe the star and take these pulses in the radio, and it's just that. All right. So the first planets were discovered with this technique, and it is the timing technique actually, and it is the principle. Okay. It is not just. It is like the magnet that I showed you. Right. So it's a very simple observation, and from that you can determine the mass of the objects supposed to be moving the star around the common central mass due to its gravitational pull. All right, so but because you don't know if the object is moving like this on an orbit, if you are looking at a jaw, or with an inclination, all right? There is a degeneracy that we call the orbital inclination degeneracy. This I is the orbital inclination angle, okay? This is the sign of the angle. So you don't actually derive the mass of the objects that are causing this motion, but you find the factor of sin I. Okay? So you find m sin I, not just s. Right? So if I is, say, 30 degrees, then the masses should be doubled, all right? But the objects are very small, right? 3.4 Earth masses, this is the Earth mass, right? And 2.8 Earth masses, so almost 3 Earth masses each. At not very close orbits in our standards, because you'll see that the planets we are observing now are at much shorter orbits. This is the astronomical unit, which is the average distance between the Sun and the Earth. So one of the objects is halfway between, and the other one is 1/3 of the road, right? So an astronomical unit. So they're not too far away. There are small, less massive objects, probably terrestrial, orbiting a neutron star. Well, back in 1992, right? The first planets. So you expect a lot of excitement, right? From the astronomical community as well as from public. But there was not much excitement because people knew that there could be no life, right? Orbiting on a planet, orbiting a neutron star, because this star had a very violent past. So it had a supernova explosion, so it expelled its outer layers very violently, all right? And this is an object emitting strong X-rays, very energetic cosmic particles, so even if these planets formed later, still from the supernova remnants, still there will be no life. So the excitement was limited. So let's not kid ourselves, we are looking for life, all right? Although us astronomers are looking for other questions, answers to other questions like how the solar system forms, what is the diversity of planets out there, which stars host planets, which stars do not, right? These are very important questions, of course, but public is interested. Planets are also like stars. Okay, this is 2 years later, they found another planet, so this is actually not just 2 sinusoidals, but 3 of them, superimposed on each other. So you have this change in the rotation period. All right, we have other discovery techniques, not just this timing of pulsars. This is pulsar timing variations. Right? There are other timing techniques that we will be talking about, but there are other methods like radial velocity, transits, direct imaging, microlensing, and astrometry. Some of them are very fruitful, so they give you 3,500 planets. Some of the others are not that productive. Nevertheless, you'll see that they are important because they allow us to probe different domains. Right? So in total, this is a couple of days ago, the number was this, and it is approaching to 5,000. Right? So remember, it started in 1992, 30 years ago. Right? In 30 years, we reached this number, 5,000. So one of the fruitful methods and one of the most important, this is a fundamental technique, is the radial velocity, and it relies on the same exact principle, almost. Okay, if you don't observe the planet, you don't see the planet, you observe the star again, right? And that star is orbiting the common center of mass with the planet. Let's assume just one planet for simplicity for the moment. Right? So stars are radiating objects, so they emit photons at all wavelengths, and those photons are reabsorbed and re-emitted in the atmospheres of the stars. So the atmospheres of those stars, which are the colder, thinner layer, are just at the outermost layer of the star, absorb the incoming radiation at certain wavelengths. then these dark lines form that we call spectral lines. Okay? They are the fingerprints of the elements in a stellar atmosphere. Okay? So they gotta be at fixed wavelengths because they just block the light at certain wavelengths only. Because I don't want to go into the details because of timing constraints. Nevertheless, the energy levels in an element, for instance, okay, are quantized. So you just have certain energy differences between the levels, the states of an atom. Okay, so these photons are absorbed by those particles, those electrons, to move from one state to another. Right? So this energy is used and never reaches you. That's why you have these dark lines. They gotta be at certain wavelengths. But if this thing is moving, when it moves towards you, you will have a blue shift. Because this is a wave. Light is a wave, right? It works like it just works like sound waves. Like when a car or a train approaches you with a certain speed, then you hear its sound shifted to shorter wavelengths at higher frequencies, so the pitch is higher. Okay, when it goes away, the pitch is lower, and you hear at lower frequencies. Okay, so this is wave phenomenon, and light is a wave. So these lines move back and forth with this motion. So what we do is to determine this motion, which we call the delta lambda. So at any given time, we take a spectrum of a star, determine the wavelengths, okay, and subtract these wavelengths from the wavelength that this line is supposed to be if we were doing the experiment in the lab, right? Say an H alpha photon has a certain wavelength, which is called its laboratory wavelength, lambda 0. That's the shift, all right? When the body approaches you, this is a blue shift. When it goes away, this is a red shift, right? This is the speed of light. What you find is the radial velocity, right? So then you take another spectrum, you determine this quantity. Then you take another, you determine that quantity again, okay? And this quantity is changing with the motion of the star going back and forth, orbiting the common center of mass. And you see this radial velocity change from one time to another, okay? Just like this. If it is periodic, it will come to the same point again, and it will repeat this again. And we know this planetary motion is working like a clock, right? It is mechanical, so it is periodic. It should be periodic. So from that, we determine if this is a very regular sinusoidal, then there is no eccentricity. So the orbit should be circular, but we can determine the eccentricity if it is a bit inclined. And we determine the semi-amplitude of this radial velocity variation, and they are coupled to those quantities. Right? Then we determine again this factor. Okay, this is the mass of the body that causes the motion. If it is in planetary mass limit, then it is a planet. It is in Browndorf mass limits, then it is a body. Right? But still, it has this factor, this annoying thing, this I. This is the orbital inclination. Alright, so we don't find the mass, but m psi. Nevertheless, we find the orbital size. This is the orbital size. This is the semi-major axis. Alright? So this is the radial velocity line. And the first ever planet discovered around a sun-like star was discovered by this method technique. back in 1995 by Didier and Michel working with the Swiss telescope at the time in Marseille. Anyway, so this is the radial velocity variation of the star they observed, which is a sun-like star. It is called 51 Pegasi. That's the star. Okay, it's a little bit larger star than our sun. It's more massive, just 11% more massive than our sun, right? So this is the radial velocity variation they first found. So they knew the semi-amplitude of the variation, which is coupled to this mass, and this mass was found to be 0.72 Jupiter masses first, but then they found out that this is even less than half the mass of Jupiter. Okay, so just to give you a scale, this is 51 Pegasi B, and this is Jupiter. Right? So it is 47 really percents of the mass of Jupiter. Okay, so they found the planet, but let me have your attention to the orbital period. The orbital period is only 4.63 days. It is less than 5 days. Right? It is. Remember, the shortest orbital period in our solar system is for Mercury, and it is over 80 days. Right? So 5 days is too small, right? Too short. And the object is rather big, right? So just very close, on a very short orbit, a massive object is orbiting. That's interesting, and this was not expected by the planetary formation theories. Right? So still, we have difficulties in explaining those. Only we explain with migration mechanisms. So they are supposed to be forming at larger distances, and they move towards their star. And they stabilize their orbits at very short periods. This is one such. And they were rewarded by a Nobel Prize back in 2019, Michel and Didier, together with James Peebles, for his contributions to cosmology. I think he's got to have the prize for himself. And because he is the founder, I think he's the founder of the observational cosmology branch. So he's very, but yeah, they shared the prize. Anyway, so this was a big deal, right? This was a big deal. Okay, so far you have seen that we can only measure, it looks like, we can only measure stars moving back and forth towards us and away from us. And the technique is, the motion causes rotation period, apparent rotation period change when we discuss pulsars, and radial velocity change when we discuss solar-like stars. Okay, so this has got to be moving towards us and away from us. So the orbital inclination should be right? So if the planet, if the star moves like this, then you will never know. You will never know, because it will not approach you. It will be moving on the sky plane, for instance. Okay? It will not be coming towards you when getting away from you, so you will never know, because it will have no radial velocity components. All right, but the position will change. Maybe we can measure this, the change of the position. Okay, this is called the astrometry technique. So it relies on the measurement of the position of the star. You expect to be moving about the common center of mass. Epsilon Eridani B, the planet, was discovered already by the radial velocity technique. But apparently, it doesn't have an edge on orbit, but it's inclined. That's why it has a radial component, radial velocity component, as well as a tangential velocity component, as we see here. So it also moves in the sky. All right? So the position changes. So people have mapped out this and found the mass, this time with absolute units. There is no Sinai degeneracy here, as you can see, because then you know what the orbital inclination is, because you know the orbital velocity, the radial component, you know the astrometric position, right? The tangential component. So this is just vector summation, all right? So you know the velocity vector, all right? From that, they determined the mass as 1.55 Jupiter masses, and it is a bona fide planet. And it has an orbital period. All right. But it requires very high resolution imaging from the ground, and nowadays from the space with the Gaia image. All right, so from 10 parsecs away, this is the Jupiter's orbital size. So Jupiter is 5 times more distance than our distance, the average distance to the Sun. Okay, almost 5 times, 5.2 astronomical units. That's what it means. All right, so these are the brightness values of Jupiter and the Sun, and this is the largest angular separation between them. So it is half an arc second. That's what you got to be measuring. From 10 parsecs away. 10 parsecs away is like 33 light years. Okay, so even the light reaches you 33 years. So they are too far away. Still, 10 parsecs is our neighborhood, right? In astronomical terms. Okay, so we found the technique, but you understand its challenges, right? And so far, only just one tentative detection has been made with astrometric technique. The others were already discovered by other techniques, like the radial velocity, and they were observed to be changing their position later on, right? So there is only one detection, so there is only one discovery, and it is a tentative one. So it is very challenging, but with the time series measurements coming from Gaia, hopefully this year, there will be many. Okay, so this is the technique that is easiest to understand, because now you are measuring the flux of the star. Okay, so you are looking at the star and count its photons. Count the photons coming from the star and reaches you. Right? If there is a body passing in front of it, then it will block some part of the photon source, the star, right? And those photons that are covered by the object will not be reaching your eye, and there will be a flux drop for some time, for the time that takes this object to travel across, right? So that's the. I'm sorry for this. I didn't realize this was Turkish. All right. So this is the time. This is the brightness. All right. So that's observation from the space. So we can determine this flux drop, and that can mean an object is passing in front of the star. This time, we are not measuring anything about mass, right? So that's the flux drop. That's this depth of this is called the light curve. Okay? That's the change of the flux that you take from the star, the energy. All right. So this is called the depth. This is delta L, and L is the flux that you take from the star. Most of the time, this is normalized to 1 by just a simple division. All right. Then you have the area covered by the object is actually pi times r squared, right? Because this is a disk. You don't see it, but it is the obstructing object, right? So that's a disk. So that's the area of that disk. And the disk that shines, that you take the flux from, is the stars. and this has an area of pi r asterisk squared. If you just take their ratio, then pi's cancel out, and you are left with this. We know the stellar radii, it is very difficult, but we know stellar radii from stellar models. Okay? These are model-dependent values. Nevertheless, we have a pretty good knowledge about the sizes of stars that we are given. All right, so this is coming from the theory most of the time, but they are calibrated measurements with smart techniques. Anyway, so long story short, we find the r, the radius of the object that is equal to that object. All right, so for the Sun-Earth duo, this is 0.1. The depth is 1%. This is not much, but you can easily measure this. So how come this has been delayed until 2000? The first transit observation was made in 2000, the year 2000. So it took a very long time. Because the probability of a transit is very low, all right? Because it has to have an orbital inclination of almost 90 degrees, so that the planet will pass in front of its star between the observer, who is an arbitrary person, or arbitrary position, right? And between the observer and the star, it has to be at the right angle. So you have to be looking at adjunct, almost, right? It's got to be more than 85 at least. All right, so this is the probability for the Earth-Sun duo. This is only 0.5%, 0.5%. That's too low, right? So if you just observe one star, maybe you will wait for nothing, right? But if you observe 1,000 stars at the same time for a very long duration, then the chances are 5 of them will be passing in front of their stars, and you will catch them when they transit. But it happens only once a year for the Earth to transit across the Sun. But you have seen that in the radial velocity, there are planets that are actually very massive objects. There's got to be also large objects with larger radii at very short orbits, right? At very short period orbits, 5 days. So you don't have to wait very long. So people designed transit experiments. They use very small telescopes, actually, 4 to 10 centimeters, just to see a large portion of the sky so that they can monitor a lot of stars at the same time, 1,000, one to catch 5. All right? More than 1,000, of course. But yes, at the same time, they wanted to observe a lot of stars. So for that, you need a large field of view, as we say. And this is achieved by very small apertures, very small telescopes. But with very, very high quality cameras, so that they can detect this tiny little flux drop. And people have found over 3,500 planets with this technique. They sent even telescopes to the space to look at the same portion of the sky for over 4 years. This is the Kepler Space Telescope, which was sent to space back in 2009, and it's continuously monitored the same part of the sky for 4 years with very high precision photometry. So they found tiny little drops in the fluxes of stars. And after that, one of the reaction wheels was broken, so the telescope was not able to observe the same part. So it was not directed towards the same point in a ways, but for 5 more years, it observed around the equator going like this, which we call the K2 mission. It even produced more than 200 planets, I think. This mission produced more than 2,000 planets and over 5,000 candidates. Okay, so now we have the radius of the objects, okay, and also the inclination. Now we know the inclination as well, right? Because the inclination should be very close to 90 degrees, then you can observe those in the radial velocity. If you can observe them in the radial velocity, then you can determine m sin I, right? Because you know the m sin I value, oops, where is it? Because you know the m sin I value and the I itself, you can determine the masses. Because you know the radius, you can determine their densities. So the object can be characterized with the combination of transit technique and the radial velocity techniques. And you know what you're observing. If it is a planet or not, you determine for sure. So this telescope worked for almost 10 years and discovered a lot of objects, but it observed very similar stars to our sun, which we call the main sequence stars. These are dwarf stars, and the location of those stars were chosen so that there are many similar stars to the sun. So it was a population study rather than a characterization study, as we call it. So it observed faint stars as well as bright ones. The bright ones were not in dominance. So most of the objects are still candidates because we can't take their radial velocities because they're too faint to observe in spectroscopy. Okay. So people sent another space telescope for that, to find planets around bright stars. This time, Kepler Space Telescope has a 1 meter aperture, so it's a 1 meter telescope. It's not small. But TESS Space Telescope, it is small. It has just 4 10-centimeter apertures. It is as big as a photographic camera lens. So it is not big, right? But the CCD cameras are very powerful, right? So it observes the sky in different regions. Each and every region here you see are observed for 27 days almost. Some of the regions are observed more than the others for a very good reason. Because this is a characterization study, so it picks exoplanets, it starts to find the exoplanets that can be characterized not just in terms of their sizes and masses, but also in terms of their atmospheres. Because with the transit technique, actually you can determine the composition of the atmosphere of the planet. Because the starlight, when it is coming towards you, some of the starlight passes through the atmosphere of the planet. And the planet leaves its fingerprints, the planet atmosphere leaves its fingerprints on the starlight. And because you know the starlight, you just subtract it and you try to find the elemental elements in the planetary atmosphere. Okay. Why it is observing more stars at the poles? Because JWST, James Webb Space Telescope, which was sent to space just a couple of months ago, December 25th to be exact, will be looking at the poles mostly. Okay? That's why it is picking stars or planets, transiting planets, to be observed and characterized by James Webb Space Telescope, so you can find terrestrial worlds. It is early to study their atmospheres, the terrestrial planets, but at least we will be able to study the atmospheres of planets smaller than Neptune, which we call mini-Neptunes, and larger than the Earth, which we call the super-Earths. So we will be studying those. Gravitational microlensing is another technique, which is very interesting. There are many physicists in this room, so they will find it interesting, I think. So you observe this time a star without a planet, a background star, which is a very faint star, too far away from you. Okay, so again, you observe a lot of stars at the same time, background stars, these are called. Okay? But stars have their proper motions as well. Okay, so stars move actually. Although this motion is tiny little, because they're too far away from us, still they move. And there are many stars out there. Sometimes they align. So one star passes in front of the background star that you are observing. Then what happens is that the foreground star that is passing in front of the background star here, the background star is moving, is actually drawn to be moving, but it's actually stationary. Okay, you are observing that star. Okay, this one, I'm sorry, you are actually observing that star. This star moves, but in order to explain the phenomenon, they fix the star and move the star that you are observing, which is fixed. Okay, so only the motions are opposite. Anyway, so you are observing that star, and the foreground star, it is a massive object. It bends the space-time around it, right? Which causes the starlight coming from the background star to focus by following the space-time curvature to reach your eye. Those photons were not supposed to be reaching your eye. They were going in other directions. But they are focused towards you because of this curvature, right? And suddenly, the star that you are observing, the faint background star, this red one, has a peak, right, in brightness, right? So, what's got to do with planets? What about the foreground star has a planet over here? Okay, when it has a planet, the planet has a mass, right? So it will also curve the space-time around itself. The curvature will be lower because it has smaller mass. The size of the curvature is coupled with the mass. So still, it will bend the space-time. And again, photons will follow, and you have a brightness boost. That's the boost due to the star, and that one is due to the planet. That's little tiny peak here, okay? The shorter one. And you find the planet. You never see that star with the planet. You never see the star. You never see the planet. So you find planets around stars that you don't see. You find, even you don't see the planets itself. Okay, so that's an interesting technique. Nevertheless, it allows us to find planets away from their stars. Remember, radial velocity transit technique, they are biased. Okay? They can detect the short orbital period planets easily because in radial velocity, shorter orbital periods, planets move the star a little bit more. The common center of mass is away from the star. And in transit, if it is closer to its star on a shorter period orbit, then it passes in front of stars many times during your observation time. So it is easy to detect them, the short period planets. With this technique, although we will never be able to study this planet, we will never be able to have its radius, density, whatever, atmosphere, forget about it. But we will know that it is there, and we will be able to find a population with planets which further away from their stars. All right? Direct imaging is another technique to help us in this way. With this technique, also we find planets away from their stars, because with this technique, this is the easiest to understand actually, not transit this one, because you image the planet. This is the planet. The first time you are seeing the planet for the first time, right? After 45 minutes, right? So that's the star, GQ Lupi, and this is the planet GQ2b. And this is the distance between the two. So what you do is try to image the planet. But it is very complicated because the star itself is very bright and the planet is very faint. So you can never, not never, but with the current technology, we are not able to take an image of the planet if it is on a short orbit. If it is away from its star, then it is possible. Okay? And in the long wavelengths, in longer wavelengths, in, say, infrared, then the star is not that bright, and the planets are much brighter because they are colder. Okay? Colder objects emit more light in the longer wavelengths than brighter objects, than hotter objects. Okay? Hotter objects emit less light. Remember the one energy distribution, right? So that spectral energy distribution is skewed towards shorter wavelengths for the star, towards longer wavelengths for the planets. So if you go towards the longer wavelengths, then you can image the planet. So you are trying to observe this in the near infrared. And the planet has got to be a little bit bright, so massive planets can be found. And also, it's got to be young to be hot. If it is hot, the planet has recently formed, then it will be hot and it will emit more photons and it will be easily detected with the large telescopes that we have today, over 4 meters size. Okay, so this is down from the ground. Okay, so that's a simulation of the solar system from 10 parsecs. So again, 33 light years away. So with the current technique, you should be able to find those things. All right. So this is let's go back to the timing technique. Okay. So although that's the subject of the talk, we already talked about it, right? So we started with the pulsar timing variations due to the light time effect, if you remember. That same thing happens with other periodic events. Okay, so with the timing technique, you have a clock-like event. Okay, so in transit timing variations, in the case of transit timing variations, which you abbreviate as TTVs, these are the transits of the planets. You have seen the transits, right? So that's the periodic events. In eclipse timing variations, ETVs, these are the eclipses of double stars, binary stars, when they are orbiting each other, around each other. You have already seen that these are the pulses that change in time, in pulsar timing variations when the case is neutron stars. And there are pulsating stars. The clock-like event is the pulsations of the star. The star changes its radius due to the physical processes, due to its internal structure. All right? So there is a clock-like event which changes in time because the thing is moving. Okay? That's it. So the idea is very simple, yet very powerful. Okay, so you have the object. Say you have a transiting planet for which you can observe the transits as an observer. You record the timing of the transit. One transit, then you observe another. After one orbital period, you should be observing another. So if there is just one planet, this should be like a clock, right? This should never change. And it doesn't actually, all right? However, if you have a third body, a second planet, say, like this one, you don't have to see it. But this system, to move about a common center of mass with the third body. Okay? So the transiting planet system that you observe, these two, move back and forth. And when they are closer, you observe the transits earlier. When they are further away, you observe the transits later. And this changes with time. This is called the transit timing variation. Okay? The same thing with the eclipse timing variations. These are two stars. When the hotter and brighter star is blocked, there is a significant drop in the light. When the colder body is blocked, the flux drops again, but it is not that deep. These are called eclipses, all right? Because these are stars. Okay? Those eclipses move back and forth. If there is a planet, say, out there, then these two will be moving about a common center of mass. When they are closer to you, you will be observing the eclipses earlier. When they are away from you, you will be observing the eclipses later. All right? So this is called eclipse timing variation. That's the variation of time. Right? Again, this is Turkish. I'm sorry. This is star 1. This is star 2. And that's the planet. All right? We have already discussed the pulsar timing variations. Then the pulses in the radio change over time due to the motion of the star. In the pulsations, this is a pulsating star because the temperature, the surface temperature of the star and its radius changes with these pulsations due to the instabilities in its internal structure. It brightens and it gets fainter, like this, okay? So if there is a planet, then this will be moving towards you and away from you, and you have the pulses earlier, have these brightness boosts earlier, when it is closer to you, and later when it's away from you. That's the same principle. Okay, so timing techniques rely on the same thing. All right, so we can find planets with this technique. Okay, how much time I have? 3 minutes? 4? 10 minutes? Do I have? Okay, so you have permissions from your family, right? Because you are staying over. No, I'm just kidding. I have just 5, 6 minutes. Okay, so we can find planets orbiting binary stars with this technique, because you have seen that one. You have seen that these eclipses will be varying in time. The timing of these eclipses will change if there is a planet around them. So you can look for planets around binary stars with this technique. We are binary stars observer. I started my job as a binary star observer. So you can observe these systems. In such systems, actually, planets can be found in different configurations. One is a planet can orbit one of the stars. Then it is called a satellite-type planet. The planet might be orbiting both stars. Then it is called a P-type planet, planet-type planet. Okay, this is the satellite-type planet because it orbits one of the stars, because it orbits two of them. This is called the P-type, and there is also a T-type, but we have never found one. These are Trojan types. Okay, so the planet could be in the Lagrangian points of the orbit of the Loma star. Okay, so there are Trojan asteroids, for instance, in the Lagrangian points of the orbit of Jupiter. So, because it is more massive than Jupiter, there could be planets out there in the Lagrangian points, although it is hard to find. Anyway, so there are 3 configurations, but there should be planets around stars, binary stars. All right, these are called circumbinary planets. Although, to me, the only circumbinary planet is this, because it's circumbinary, right? This is not circumbinary, but still, we call all of them circumbinary planets anyway. Okay. Okay, so what we have done is finding 2 new joint mass exoplanets around one such system, which is Kepler 451 This is a binary system in, obviously, the Cygnus constellation, because Kepler was observing the place. So this has a Kepler catalog name, because the Kepler telescope was observing it. Not just because it was observing it, it has a Kepler name, but also another team has already found a planet-sized object orbiting this system. So it was already known to be hosting a planet, which is Kepler 451b. Right? So when we name planets, we do a funny thing. Okay? We take the catalog name of the star. This is the star. Right? This is the star. We don't use A, we reserve it for the star, the letter A, we reserve it for the star, but we never use it for the star as well. But we reserve it for the star for some reason that I don't know why. But we use B for the first object that we discover around. Right? So 451b is the first planet that we discover around the system. Okay? So this was already found by André Baran and his team from Poland back in 2015. So this system was already known to host the planets. We found other 2 planets in the system. All right, that's our team, and that's the paper, which was published just a month ago in Monthly Notices of the Royal Astronomical Society. If you want to know what is the star, where is it, and what it looks like, it is an ordinary star here. You can never see it with your naked eye. It is too faint to be seen. 13 magnitude star, so it is pretty faint, right? It is over 1,300 light years away, so it is too far away, okay? So the light that we see now has departed the star this many years ago, okay? When Göktürk was on the scene on the Earth, right? So for the first time. So the planets that we found have that time of their life. All right, it's in Cygnus constellation, Ku in Turkish. All right, this is an eclipsing binary system, obviously. Okay, the M is a dwarf cold star with the spectral type M. And this is the STB subdwarf B type star. B means it's a hot star, okay? But it's not a dwarf star, it's a very small star. It's interesting, but we are going to be talking about it later. All right, the orbital period of the eclipsing binary, so this DM star, which is a small star, and this STB star orbits around a common center of mass in 3 hours. In less than 3 hours, actually. Okay? So they are very close to each other. Okay, so the light curve, the change of the light is such. Okay, say this is the STB star, this is the dwarf M star, which has got to be red, actually. This blue is very good, right, because it's a hot object, but this got to be red. And when this subdwarf star is eclipsed, there is a huge flux drop because this is hot and very bright, so the photons also warm. When this is occulted, because it is cold and faint, the flux drop is on the side. So that's the light curve.
Should the orbital period of this star be same?
Sorry?
Should the orbital period be same?
Yes, exactly. They orbit the common center of mass with the same period.
But if you make an analogy to springs around the center of mass, they have different masses, so should the period be different?
No. It's the same as the solar system. Okay? So we orbit the sun in 1 year. The sun orbits the common center of mass with us in 1 year as well. Okay? But on a close orbit. Okay? So that's got to be derived from celestial mechanics. Okay? So you will have a really light over here if you want me to explain this. Alright? Okay, so that's the light curve. That's the light curve. The orbital period is from one, this is called the primary minimum, from one primary minimum to the other, which should be, it should be constant if there were no planets, if there were no other bodies. But this is not constant, this is variable, as you can see. Okay, that's the light curves that we have with our 80 centimeter telescope in Ankara, which is not too far away from here actually, our brand new telescope, okay, in different bands. This is from, I think this is from TESS, the telescope on orbit, and this is from Kepler. Right, so we modeled those, derived the parameters of the companions. So it turns out that the STB companion has this surface temperature, almost 30,000 kelvins. So 5 times hotter than the sun, to give you a scale, but in half the mass of the sun. Okay, 0.48 solar masses. So it is a small star. These stars are interesting in their own right because they were actually stars larger than the sun, but because their core become degenerate before fusing helium, they expelled outer layers. But these, if they were not in a binary system, okay, if it is just an isolated star, then it will expel its outer layer to the space. But because there is a companion over there, it will transfer its mass to the companion. But companion cannot accrete all the mass, so this mass is forms a disk, what we call the accretion disk, around the binary, and it actually covers the entire geometry, and then we call it a common envelope. So this gas that is expelled, the outer layers of a larger mass, a larger star than the sun, covers the 2 stars actually in a common envelope. Okay, so this is called the common envelope case. Anyway, so this is the DM companion. It is very small, right? 0.12 solar masses only. So this is pretty much 120 Jupiter masses. Remember, 80 Jupiter masses is the lower limit for stars. So it is pretty close to the lower limit for stars. And it is a very cold object. I know planets hotter than this. Okay, so this is, although it is a star, it is pretty cold. And it is a small one. This is also small and less massive because it is expelled out. It's got to be much, much larger object. And it is hot because we are looking at the inner structure of the star actually, because the outer layers are gone. We are looking in the inner layers, which are hot. Okay? So that's an interesting system. So this is the orbital period, and this is the orbital size. Just 90% of the solar radius, so it will be inside the sun if it was here. Okay, the binary. Okay, so we determined these timings of the eclipses very precisely from Kepler space satellite, from TESS, from our observations, and we formed what we call the O-C diagram, which is pretty simple actually. This is the time. This is the variation in the eclipse time. Okay, so the eclipse times change. If there were no bodies, it will be constant. But it is changing, you see. So that change, this blue one, has a periodicity of over 400 days. 416 days was suggested by Andre Baran back in 2015. So it is Kepler 451b. So we confirmed this planet first. Okay? So it is there. It's got to be there. Okay? We observe the same thing. On top of it, see, there is a longer periodicity. Okay? When they are combined in this red continuous curve, okay? it is the best model, it is our best model. It has an orbital period of 1800 days, 1000 days and 800 days. Okay? So it is a longer duration thing. Okay? And these test observations, these are test observations, and our observation give the scale. Okay? Here. So it didn't go like this, which was expected by Kepler observations, but it turned back and went like this. And we understand this from test observations and our own observations. And then we model them. This is the orbital period we derive. Okay? So we found the larger period planet, Kepler 451c. Okay? That's the second planet. So C comes here. That's the first planet we found. All right. Then we just subtract the data from the model. Then we get the residuals. These are the residuals of the Kepler data here and other data here. Then we had a frequency search in the residuals. If there is a periodic variation in the residuals as well that we are not aware of. And there is a peak here. This is just a Fourier transform. This is just, you know this, right? You got it. Okay? If you don't, you will learn. Okay. So that's the peak in the Fourier domain. That's the frequency in the residuals of the data, which corresponds to 43 days. All right, there is a signal here, so we are excited. Actually, we found another dominant signal at over 3 days, but it turned out that it was the sampling frequency beating with the orbital period. It is interesting because Kepler takes data points once every minute. Okay, once every minute, it just puts that data point in the light curve. All right? But because the orbital period is an integer multiple of this sampling, okay? So after 30 orbital periods, you go back to the first point again, okay? So say 1 dot here, 1 minute later, another dot. 1 minute later, another dot. 1 minute later, another dot, okay? After first orbit, the data point is a little bit shifted, okay? After the second orbit, it's a little bit shifted. After third, it's a little bit shifted. But after 30th orbit, it comes back to the same point again. Okay? And 30th orbit is almost 30 days. Okay, 3 days, I'm sorry. Okay, so interesting. We found the sampling frequency. So we eliminated it first, and then we renewed our frequency search and found this peak, which is at 43 days. And when we phased our Kepler light curves with this frequency, yes, we have another signal. Okay? With a very low amplitude. This is the 451D at orbital period 43 days, so we have the D. So we discovered the second planet from the frequency analysis. Okay? Andre will not be able to see this periodicity because he was limited with these observations. But I don't know why he was not able to find this frequency. Actually, I know why, but he could have. Because Andre is an astrophysicist who is interested in SDBs for their own right. So he works, he doesn't work on the ETVs, he works on he tries to understand the physics of the subdwarf binary, which is a pulsating star, by the way. So it has its frequencies, and he was trying to model the star itself, not the eclipse timings. But what he did was different. That's why I think we were able to recover this thing. Anyway, so these are the planets. This is Kepler 451a. This A, capital A, is this SDB star, the first star in the system. See? This is the A. But capital B. Capital B is for the DM star, the other star, okay? the companion, the smaller, colder star. Capital B. AB, D is the shortest period the shortest period planet here. Because we found it later than the longer period planet here, it is called D. Okay? So Kepler 451d or ABD, this tells you that this planet orbits both of the stars. So it's a planet-type planet, P-type planet. Alright? Alright, then the C, but we abbreviate and we never use this AB. We call it this way. Okay, so this is the first planet that we found after Baran, and that's Andra Baran's planet. We just updated the periodicity to 406 days, 10 short, than they had found. All right, this is our pretty picture. All right, so bear in mind that these are not real, right? Because we never see the planets. Okay, so we only see the stars and study the starlight only. But this should be the system here. You never see the DM. You don't see the DM, by the way, in the spectrum nowhere. Okay, you don't see the cold star. This is the short period orbit planet. This is what Andra found. This is the long period orbit planet, and that's the system. So we publish the results. But there is a verification test, actually. Okay? What if dynamical effects cause the orbits to be unstable, and they were never there? This happens. We study such systems, and we actually found a system suggested to host two planets, and we found out that they cannot be there because those orbits are not dynamically stable. So the gravitational pull of the objects should cause those orbits, should cause those bodies either to be ejected from the system or to crash on each other. All right? So actually we just rejected two planets suggested before first, but it did not attract much attention from the community. But when you discover two, then it attracts more attention. All right, so we try to look at if the orbits are stable. This is the orbital stability map of the system. The blues are the configurations for the third body for this system to be stable, and these are the unstable configurations. And our best solution is here. This is 1456 days or so, okay? But the orbital stability test tells us that the orbital stability can be satisfied on a longer orbit, and there is an alternative solution for the ETV diagram there, which I showed you, okay? And this gave us the orbital period of 1800 days. So this 1800 days came from the orbital stability test, okay? That's not the best solution, that's the second best solution. Nevertheless, it is stable, okay? The planet's got to be there. All right, so we found the planets. Became famous for 2 days, and it's over. So, and my presentation is over.